So in the previous lecture, we were trying to understand the relation between symmetry and chemical bonding. So in this lecture, let us continue that discussion and see what are the two most popular theories which describe chemical bonding. So we'll go to lecture 36 and we will continue our discussion of symmetry and chemical bonding. So bonding can be described by, again, this you must have already read in your first or second year of BSc. So it's valence bond theory, and second is molecular orbital theory. So this is also denoted as VB, and then this one is as MO theory. So now let us discuss first the valence bond theory, and then we will try to use symmetry arguments to develop the bonding wave functions in valence bond theory. Okay, so let us discuss what are the salient features of valence bond theory. So basically it is an extension of Lewis' idea of bond formation through sharing of electrons, right? So electrons are shared to form a bond. Then electron sharing is presumed to be localized. Localized between the pair of atoms which are interacting to form the bond. Then what is the next point? It's the orbital interaction and the bond linkages. So there is a strong correlation between orbital interaction and bonding linkages. So this is only to refresh the previous lectures which you must have read about valence bond theory, and that is in a diatomic or a polyatomic molecule, right? And then electron density between the pair of atoms is described by a new wave function, which is the product of the wave functions of two interacting orbitals. And fifth is shape of the molecule. How do you define the shape of the molecule? The shape of the molecule is understood from VSEPR theory. I'm not going to go into details of what that is. That is, we'll just briefly say, on the basis of minimization of electronic repulsion and consideration of atomic sizes. Alright, and I think the last point is electron density between pair of atoms associated with a bond is the result of effective overlap of appropriately oriented. So this is very important, that they must be appropriately oriented, because then only they will be able to define the shape of the molecule, right? Atomic orbitals. And this is where the problem is, because atomic orbitals are oriented along Cartesian coordinates and they do not generally orient as per the shape of the molecule. We can say leading to a particular length and strength of a bond. So why this is required? So consider that you have atomic orbitals which you want to overlap or interact with other atomic orbitals, and then resulting into a given shape of the molecule, right? So now this is not always, these atomic orbitals are, as I said, not always oriented along the shape of the molecule. So we can say now the need of appropriately oriented atomic orbitals consistent with the molecular shape, consistent with the molecular shape is difficult. This is because atomic orbitals are oriented along the Cartesian axis. Along the Cartesian axis, and not with respect to molecular shape, and thus effective overlap is not possible. So let us consider a case of carbon. So the electronic configuration of carbon can be understood as 1s2, 2s2, 2p2, right? So now I'm trying to form bond between CH4. We know that the shape of the molecule is tetrahedral. So that means all four bonds, all four CH bonds must be equivalent. Now if 4 hydrogen bonds come with 4 s orbitals, then the combination happens between this s orbital and the empty p orbitals. So now all the bonds form will not be same if we just combine atomic orbitals of carbon with atomic orbitals of hydrogen, right? So hydrogen has 1s1, right? So these are not effective overlap, and this will not intuitively lead to a tetrahedral shape. So then now what do we do? What is the solution for this? So Linus Pauling actually came up with solution, and he proposed hybrid orbitals. Like we have learned that how carbon is sp3 hybridized in CH4, right? So carbon is sp3 hybridized, leading to a tetrahedral shape, and carbon is sp3 hybridized or sp2 in other molecules, or sp hybridized in other molecules, right? So there is a concept of hybridization where atomic orbitals mix and match, leading to formation of hybrid orbitals which are now equal in energy, and thus they interact with the atomic orbitals of hydrogen, leading to formation of tetrahedral shape, right? So we can say that the hybrid orbitals are best for explaining or for describing the bonding and the molecular shape of CH4, whereas atomic orbitals of carbon are best to describe a single carbon atom, right? So this we can understood now. So let us now see how symmetry and group theory arguments can be used to develop what atomic orbitals can be mixed to give you a hybrid orbital, okay, which will satisfy the tetrahedral shape of the molecule. All right, so let's go there. So let us start with four tetrahedrali oriented equivalent hybrid orbitals. So we start with the assumption that these hybrid orbitals exist, and we will represent them with vectors psi1, psi2, psi3, psi4. Let us see. So for a tetrahedral, I am going to draw a cube because then it will be easier to understand. In the center of the cube is the atom, and then you have four hybrid orbitals which are now represented by the arrows, right? Now these arrows are oriented as a tetrahedral, right? So this angle will be the standard 109 degree 28 minutes between these. Now let us represent them with psi1, psi2, psi3, psi4. Okay, so now here we are assuming that these orbitals are already existing. Orbitals exist, and thus they will form bases of for a representation in TD point group, right? So now let us create representation under TD point group. So this is my TD point group, and I'm going to write the operations classified into different classes: E8C3, 3C2, and I have 6S4 and 6 sigma Ds, right? Now tau for size, psi1, psi2, psi3, psi4. Now we will use the same rule where we'll say that upon carrying out a symmetry operation, if none of these change, then they will contribute to trace. If any of this will change, then it will not contribute towards the trace. So then E will have a trace of 4, each of the C3 will have a trace of, so only one of the psi1 or psi2 will not change because that will be the C3 axis. So I will say 1. C2 everything will change, so 0. S4 everything will change, so 0. Sigma D 2 will not change, right? All right. So now if I use reduction formula, use reduction formula to reduce tau psi, and this will result into A1 plus T2. So now we know that we have 4 hybrid orbitals which give us the representation as tau psi. Tau psi upon reduction gives me A1 plus T2, right? Now A1 is the totally symmetric representation. A1 is totally symmetric representation. This means that A1 has same symmetry as that of s orbital, right? It can be 1s as well as 2s. Both of them will have same symmetry, s orbital. Now what about T2? So T2, if we look at the character table, so from character table, we see that X, Y, and Z jointly form the basis of T2. That means that I can say Px, Py, Pz orbitals will have T2 symmetry. Now if we also see that Xz, this is again from character table, Yz and Zx, they will also form basis for. So this comes from the unit vector transformation and this comes from the binary products. Okay, so this is from unit vectors and this comes from binary products. Binary products as the basis, right? So this tells you that dxy, dyz and dzx orbitals will have T2 symmetry. Okay, now there is a confusion between what to combine. Okay, so 1s orbitals cannot combine with, so we can say, let us say what we have. So we have principal quantum number as 1s, 2, then we have 2s2 and 2p2. So we have 2s orbital here and 2px, 2py, 2pz orbital here. Then we have 3s orbital which is empty, 3p orbital which is empty, and 3d orbital, right? I mean, there is no point considering combination of 3d orbital with 2s orbital because there will be a lot of difference in the energy, right? This will be very high in energy, so you cannot combine this with this. Now, similarly, this s and this p cannot be combined. So we only have to combine s and p or s and d orbital because A1 has S symmetry and T2 has either Px, Py, Pz or Dxy, Dyz, Dzx symmetry. So either you can combine, see this combination is meaningless because there is no electron in that, right? So if we are trying to combine, so this does not work. So if we are trying to combine this, this also does not work. If you are trying to combine this, this also does not work. The only combination possible is the only this also does not work, right? Possible combination is 2s and 2p orbitals, right? So we have 1s orbital and 3p orbitals, which can now combine to give you 4 hybrid orbitals, psi1, psi2, psi3, psi4, right? So now if we apply projection operator, so apply projection operator. So I'm not going to go into the complete calculation. You should be well versed with this now. So if we apply projection operator, I'll have to do PA1 onto psi1, right? This will give me psi1 plus psi2 plus psi3 plus psi4, right? And then upon normalization, you can say that this will be half. So similarly, if I do PT2 on psi1, you will see that I'm leaving this exercise for you to do it at home. So you will get 3 psi1 minus psi2 minus psi3 minus psi4, right? So what are the other two orbitals? So if we now try to do it for psi2, you will get the similar combination with 3 psi2 minus psi1 minus psi3 minus psi4 again. So they will not be orthogonal to each other. This and this, let us call this as phi1 and phi2. So these two are, let us say this is phi1, this is phi2, okay? So phi1 and phi2 are orthogonal. So you can take the dot product and take the summation over all size, and it does go to 0. But the other phi's which you will get upon projecting out onto psi2, psi3, psi4 will not be orthogonal to each other. So now what to do here? So if we carefully see, this is actually, instead of a combination of 4 psi orbitals, we have, what we have is 3 here and 3 here. So 6 psi orbitals are interacting with each other. So right, that is not a favorable case because you have more than expected orbitals. So now if you see that this can be broken down into linear combination of 3 independent orbitals. So psi1 minus psi2 minus psi3 plus psi4, psi1 psi1 plus psi2 minus psi3 minus psi4 and minus psi2 plus psi3 minus psi4, right? So if you take this summation, you will get this back. So now I can call these as phi2, phi3 and phi4 and not this one. So now if you see that these are orthogonal to each other as well as orthogonal to this one. So 2 positives and 2 negatives. So these two will be orthogonal. And then here if you see that there again there are 2 positives and 2 negatives. So this will also be orthogonal. So you can test it out. Now if we see that this one has a symmetry. So phi1 has a symmetry of s orbital. So I can equate the symmetry and I can say that this is my half psi1 plus psi2 plus psi3 plus psi4, right? Similarly, I can say px, py and pz will have symmetries corresponding to rest of the 3 phi's 1 by 2. So psi1 minus psi2, psi3 plus psi4. Then I have psi1 plus psi2 minus psi3 minus psi4. Then I have psi1 minus psi2 plus psi3 minus psi4. Now if I try to write this in matrix form, I can always say S px py pz is equal to psi1 psi2 psi3 psi4, right? And this will be my half. I can take outside. This is 1 1 1 1 1 minus 1 minus 1 1 1 1 minus 1 minus 1 1 minus 1 1 minus 1, right? So now if I want to write in terms of psi, what are the combinations of s and p orbitals? So I can always say that psi1 psi2 psi3 psi4 is equal to half 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 minus half plus half and the inverse of this. So this is so on. So you can write the rest of the components. So you have S px py pz, right? I can always say that. Now this implies, so I can write psi1 is equal to, if I expand this, take this inverse, I can always write this as psi1 is equal to S plus px plus py plus pz. Psi2 as S minus px minus py plus pz. Psi3 as S plus px minus py minus pz. Psi4 as S minus px plus py and minus pz, right? So now you have expressed hybrid orbitals which you assume to start with that they exist in terms of atomic orbitals, right? Now you know the symmetry of these orbitals. From there you have now deduced that what atomic orbitals should combine to give you 4 hybrid orbitals which will be oriented along in a tetrahedral fashion, so that you can combine now these psi's with the hydrogen atomic orbitals, right? So now if we want the formation of the bonds, so you can express those bonds in terms of psi1 into 1s1, psi2 into 1s1 of A, B, psi3 1s psi4 1s-d, right? These are the hydrogen atomic orbitals and these are the carbon hybrid orbitals, right? So using this you can form 4 bonds which will now define the correct molecular shape, right? So this is an example of how valence symmetry and group theory can be used to explain bonding under valence bond approach, right? So now in the next class we will go forward with this chemical bonding and we'll look at the localized and delocalized molecular orbital picture and how symmetry and group theory can be used to describe bonding in those cases. All right. That is all for today. Thank you.